Hola amigos, so now let's move on to our next topic, that is 7.3 of Introduction to Flight book we are following, and chapter 7 topic 7.3, that is movements on the airplane. So here you can see the airfoil, or you can also assume it to be a wing of the airplane. So on the wing or the airfoil, the forces are represented. The aerodynamic forces you can see over here are the lift and drag, and they form a resultant R as shown by the dashed line, a vector R. And if you observe, the lift force is perpendicular to the free stream V infinity horizontal velocity, and drag force is parallel to V infinity. And if you closely observe, there is a movement about the quarter chord point, that is at 1/4 of the chord line, which is represented by capital M subscript C by 4, quarter chord C divided by 4. And this movement is because of the change in angle of attack of the wing. So as the angle of attack changes, the movement about this quarter chord point also changes. So if you analyze the movement on the wing, it will keep on changing with angle of attack, and for every point on the chord line the movement will be different, and there will be a different variation of movement with angle of attack. But there is a point on this chord line at which the movement about that point does not change with the change in angle of attack, and that point is known as aerodynamic center. In thin airfoils, it is assumed to be that aerodynamic center is equal to the quarter chord point, or aerodynamic center is at quarter chord point. But in the wings, aerodynamic center is not at quarter chord points. Okay, so we will be learning about this in depth in just a little while. Okay, so let's see the next figure now. Here you can see that the lift and drag forces have components in the normal and axial directions, that is in the direction of N and A. Okay, as if you draw the normal N perpendicular to the chord line and parallel to the chord line A, then the component of forces lift and drag forces will give you the normal force N and axial force A. Okay, so this is the aerodynamics part that we will be using in our topic, that is movements on the airplane. So just be with me. And here you can see that this is a kind of pressure distribution on the airfoil. Okay, so over here we are seeing that there is only the pressure distribution which is shown, but in reality we know there are this shear stress forces are also there, but only pressure distribution is only shown over here for the time being. So what happens, because here we are more concerned about the lift force actually for the time being. So what is happening over here is that this pressure distribution around the wing or here airfoil is showing you the magnitude of forces that can be replaced as an equivalent of this pressure distribution as shown by F1 and F2. Okay, so this pressure force around the airfoil can be represented or substituted by these F1 and F2 forces at point 1 and 2 as shown over the airfoil. So if we want airfoil to generate lift, then F2 force should be greater than F1 force. And if you observe, they don't act on a single point, they act at two different points, 1 and 2. So they create movement. Okay, so because distance between two opposite applied forces will create a movement about a point. Okay, because they will form a couple and it will create a movement. One more thing to be noted over here is that the below pressure lines are greater in length as compared to the pressure lines above the airfoil, which shows that the pressure force below the airfoil is more than the pressure force above the airfoil. So and also if you observe that more of the pressure lines or length of the pressure lines is greater at the leading edge section of the airfoil. So and in general it is observed that the lift force is around 80 to 90% of lift force is generated by the leading edge section of the airfoil. Around near the leading edge of the airfoil, you will observe that 80 to 90% of the lift is generated, and the rest of the lift is generated by the back portion behind the leading edge. So coming on to the movement part. So now we know that force F1 and F2 create movement. Okay, so because they are creating a couple which creates a movement, and if the distance between force F1 and F2 increases, then the movement will also increase, or the couple formed by force F1 and F2 will increase. But if the distance between F1 and F2 remains the same, and this couple is translated at any point or any location within the airfoil on the chord line, then this constant value will not change, because this movement F1 F2 or the couple F1 F2 is constant, because the distance between F1 F2 does not change and it will remain the same. It is very important point to be noted that this constant movement value can be translated anywhere on the chord line. Okay, and this concept will be used extensively in analyzing the movement about CG actually, or you can translate this movement anywhere on the airplane itself, not only on the wing, anywhere on the airplane. It will remain the same because it is a constant value. So one more thing you need to know about this is that if F1 and F2 forces remains the same, then the net force will be 0, which means the lift force will be 0. And at that point, the amount of movement created by the lift force is 0, but the movement or the couple, because of the separation between these two forces, will be there. So the amount of movement or the movement which is created when lift is 0 is also known as moment about aerodynamic center. So the point which we were discussing earlier, that here it is quarter chord point about which movement is given by mc/4, which will change with angle of attack. But here the movement about aerodynamic center will not change with angle of attack, and it is the same movement which is constant at 0 lift, and hence this movement can also be translated at any point on the airplane, and this movement is at 0 lift. And here we can see the significance of movement on the airplane. Why we are learning about the movement on the airplane? Because any kind of disturbance in the forces that are keeping the airplane in equilibrium state, that is the lift drag forces are keeping the airplane in equilibrium state when flying at angle alpha e in the horizontal direction v infinity, in the direction of v infinity. Then if the forces are disturbed by the gust, then these lift and drag forces will change, and they will create a disturbance, which is the increase or decrease in the movement about the CG of the airplane, which will destabilize or change the equilibrium state of the airplane. As you can see over here, the angle of attack, that is equilibrium angle of attack alpha e, is changed to angle of attack alpha over here because of the gust, vertical wind force that acted on the nose of the airplane. It increased the lift and changed the equilibrium state from bold airplane position to dashed airplane position, and we want the airplane to come back to its bold airplane equilibrium state. If it's stable, it will come back, but it will have tendency to come back if it's statically stable. Okay, so now let's see the forces that are acting on the airplane. So the forces are aerodynamic forces, lift and drag, thrust force T, lift force on the tail as well, wing. We have just saw this lift drag forces, and the movement about the aerodynamic center AC. It is shown clockwise over here, and weight of the airplane, which is acting about the CG of the airplane. The point to be noted over here is that weight force will never create a movement on the airplane because it is acting on the line of action of the CG. Okay, any force acting on the CG will not create a movement about the CG, because if the distance is 0, so the movement about the CG is 0. If you observe here, the lift force on the wing has a distance from the CG and it is creating a movement. But if lift force is brought to the CG of the airplane, it cannot create any movement. Okay, the main point I want to introduce over here is that if you observe here, we have represented the aerodynamic forces lift and drag on the quarter chord point at c/4. Okay, therefore you are seeing the movement here as c/4. But here, if you see, the lift and drag forces are acting on the aerodynamic center, and the movement which you are seeing over here is movement about aerodynamic center, which is clockwise shown over here, because clockwise movement is taken as positive. But in general, the value of coefficient of movement is always negative. Okay, so the lift drag forces will create movement about the CG, and an airplane can be brought to an equilibrium position by controlling the amount of forces, lift and drag forces, okay, by deploying or deflecting the flaps according to the desire of the pilot. And the thrust force can also introduce movement about the CG if it's not in the line of CG. Okay, so here okay, just a second. So here you can see what I was saying about aerodynamic center. Aerodynamic center for the wing, you can read the theory that it is a point on the wing which about which the movement does not change because of the change in angle of attack, and movement about aerodynamic center is given by q infinity sc times cmac. Cmac is coefficient of movement about aerodynamic center, and therefore cmac is equivalent to movement about aerodynamic center divided by q infinity sc. Q infinity is half rho v square, which is the dynamic pressure. Okay, so at 0 lift we know the movement about aerodynamic center, or at movement about any point, remains the same as we just discussed, because the distance between these two forces is not changing. Okay, so if the distance does not change and the amount of movement that this couple is generating is translated at any point, then the movement about any point is same as the movement about aerodynamic center, which is the movement when lift is 0. Okay, so and the next thing is at 0 lift, the movement about quarter chord point is also equal to the movement about aerodynamic center, which means their coefficients will also be the same. That is, coefficient of movement about aerodynamic center is equal to the coefficient of movement about quarter chord point at 0 lift is equal to the coefficient of movement about any point at 0 lift. So you can read this. Okay, so here it is shown that when the wing is at 0 lift angle of attack, which is negative angle of attack, at which the lift is 0, then the amount of Cm AC, or the value of Cm coefficient of movement about any point, is the coefficient of movement about aerodynamic center, which does not change with the change in angle of attack. Okay, here it is clearly shown that CMAC is constant for angle of attack. So aerodynamic center is very useful concept for the study of stability and control, and it is this reason that we substitute quarter chord point. We don't substitute, but we use aerodynamic center for representing the forces, aerodynamic forces at quarter chord point. Okay, we do not represent forces at quarter chord point or center of pressure, but we do represent aerodynamic forces at aerodynamic center, which is AC, because the movement about that point does not change with angle of attack. Okay, so with this I would say that movement about CG can be given by CMCG Q infinity SC, and hence you can determine the coefficient of movement about CG as movement about CG divided by Q infinity SC. And here one more thing, or the last thing I would like to say, is that I have talked about trimming of airplane earlier, and this is the last thing, that here the airplane is in the equilibrium state at alpha E angle. Okay, and it is flying horizontally in the V infinity direction. Okay, so if you want to fly the airplane in the dashed position or dashed equilibrium state, then you have to use the elevators, and it will increase the lift and change the moment for that instant, and it will bring the change that is going to increase the equilibrium angle alpha E to angle of attack alpha, and will bring the airplane from solid line over here to dash line. And this thing is known as trimming of the airplane. That is, earlier aircraft was trimmed at alpha E angle, and now the aircraft is trimmed at greater angle, which is alpha, and it has attained a new equilibrium state, which is the dashed airplane state, and that is because of the change in movement about the CG of the airplane, which is why we are concerned about the movement about the CG of the airplane, which makes the airplane stability, which accounts for the stability of the airplane. Okay, so we will continue in the next lecture.